I am going to talk about stress and curves and plastic deformation. I am Dr. Narayanasamy, retired professor, Department of Production Engineering, National Institute of Technology, Tiruchirappalli, Tamil Nadu, India. My email address is given here, narayan19355@gmail.com. This figure shows the engineering stress strain diagram for tensile test. This along the y-axis stress is taken, along the x-axis strain is taken. Stress strain curve for a ductile metal. This shows the stress strain curve, engineering strain curve for the ductile metals. The true stress increases with increasing strain. Stress increases with increasing strain up to the elastic limit in linear way. Here elastic limit is, this is the elastic limit. After that this is your yield stress. This is elastoplastic deformation. Here the stress increases with increasing amount of strain. This is according to strain hardening. Sigma equal to k epsilon power n, where sigma is the true stress, epsilon is the true strain, k and n are constant. This is the maximum load point or ultimate tensile strength. After that necking takes place. Void nucleation takes place. Then void growth may take place. One void may join with another void, that is called void coalescence. Then load carrying ability is lost and the fracture takes place. This is your uniform plastic deformation. Where volume constancy principle can be obtained. That means volume before deformation is equal to volume after deformation. Here, this is non-uniform deformation, non-uniform plastic strain. This is uniform plastic strain. This is non-uniform plastic strain. Here, volume is not constant because of presence of voids and etc. So, mass constancy principle can be applied. Up to the elastic limit, it is elastic deformation. After elastic limit, the material will deform plastically or plastic deformation takes place. Uniform plastic deformation is between elastic limit and ultimate tensile strength. Non-uniform plastic deformation after UTS, ultimate tensile strength. In tension, this is non-uniform deformation is called necking. This is unstable flow. Strain hardening. The stress strain curve that is known as flow curve in the region of uniform plastic deformation does not increase proportionally with strain. This material is said to be work hardening. Work hardening takes place or strain hardening takes place in this region. An empirical mathematical relationship was advanced by Hallman in 1945 to describe the shape of this engineering curve, where sigma equal to k into epsilon power n, where sigma is the true stress, epsilon is the true strain, k is the strength coefficient, and n is the strain hardening exponent. One can obtain strain hardening exponent value from a log plot of stress versus strain. Next. Strain hardening exponent. Strain hardening exponent is given by d of log sigma d divided by d of log epsilon, or d of ln of sigma d of ln of epsilon. So you will get sigma by relationship, you will get sigma epsilon by sigma divided into d sigma by d epsilon. Whereas n equal to 0, it's a perfectly plastic solids. When n equal to 1, it is a perfectly elastic solid. N varies from 0.1 to 0.5 for most of the ductile metals. Strain hardening rate or work hardening rate. D sigma by d epsilon is work hardening rate or strain hardening rate, that is given by n into sigma divided by epsilon. Using this expression, strain hardening rate can be determined. This figure shows the force versus extension diagram for ductile metals, or instead of force you can use, if you divide it by force by initial area of cross section, you will get engineering stress. This is delta L is extension, E is the L minus L minus L by L0 divided by L0. This is engineering strain. Here the stress value increases with increasing strain linearly. Once it crosses the yield point, the onset of plastic deformation takes place. Beginning of plastic deformation takes place. Here, uniform plastic deformation takes place up to this point, maximum load point or UTS point. After that, non-uniform deformation takes place because of presence of nucleation of voids, etc. Ultimately, load carrying ability is lost. Finally, fracture will take place. This is the typical tensile sample. L0 is the initial length, initial area of cross section is A0. So after deformation, Li increases, AI decreases. Once necking starts, Li increases drastically, AI also decreases drastically. So this is the region, narrow region. This narrow region, necking takes place. Necking takes place in this narrow region. Why does necking occur? We can explain these things mathematically by considering the strength increases caused by strain hardening and reduction in cross-sectional area caused by Poisson effect. During the plastic deformation, the load carrying capacity of the material increases as the strain increases due to strain hardening or work hardening. Strain hardening or work hardening is opposed by gradual decrease in the cross-sectional area of the specimen as it gets longer. At maximum load, that is UTS, ultimate exertion, on the stress strain, engineering stress strain diagram, it is required increase in stress to deform the material further exceeds its load carrying capacity. This leads to localized plastic deformation or necking. This necking represents unstable flow, unstable deformation. Here this is the tensile sample. This is initial gauge length L0, initial area of cross section A0. So as the deformation continues, Li increases, Ai decreases. Once the necking starts, deformation is restricted to the narrow band. So Li increases drastically, Ai also decreases drastically. Here, the material cannot sustain the increase in the stress required to continue deforming and work hardening it. Criteria for necking. Let us start by considering the amount of force dF that is required to deform the specimen by d epsilon. We know that a force is given by sigma into A, where sigma is stress and A is the area of cross section. The slope of the stress strain curve is given by dF by d epsilon equal to sigma into dA by d epsilon plus A into d sigma by d epsilon. Here, please note that we are here using this stress strain diagram. This is true stress and true strain values rather than engineering stress and engineering strain. This is engineering stress, this is engineering strain. So we are using true stress and true strain values. D sigma by d epsilon is the work hardening rate. It is slope of the stress strain curve. It is always positive. dA by d epsilon is the rate of geometrical softening, the rate at which the cross-sectional area of the specimen decreases with increasing strain due to constancy of volume. It is also negative. Local decrease in area that causes the region to strain harden locally relative to the rest of the cross section. The remainder of the cross section deforms until the uniform cross section is re-established. The right balance of ultimate tensile stress is given by dA by d epsilon equal to d sigma by d epsilon. When dA by d epsilon is greater than d sigma by d epsilon, deformation becomes unstable. That is after nicking. The material cannot strain harden fast enough to inhibit nicking. Criteria for instability is defined by this condition where the slope of the force distance curve is equal to 0. dF equal to 0, we know that at maximum load. We know that F equal to stress into area, where F is the load, sigma is the true stress, area is the area of the maximum load. dF is given by differentiating on the both side. Differentiating on the both side, we get dF equal to sigma into dA plus A into d sigma. At maximum load, dF is equal to 0. So that's why dF equal to sigma into dA plus A into d sigma equal to 0. Recalling the deformation constant volume process, thus we will get L into L0 into A0. Initial length into initial area of cross section equal to LA is a constant. LA is a constant. Differentiating on the both sides and rearranging will get dl by L equal to minus dA by A equal to d epsilon. So if we invoke instability criteria from the above equation, we get dA by A minus dA by A equal to d sigma by sigma equal to d epsilon. Thus, at the point of instability, d sigma by d epsilon equal to sigma when necking occurs. If we incorporate engineering strain E in the equation presented above, we can develop the more explicit expression. D sigma by d epsilon equal to d sigma by dE into dE by d epsilon. Here, d sigma by dE, dE can be written as dl by L0, d epsilon is written by dl by L. So L, dl get cancelled each other. We will get d sigma by dE into L into L0. This is L0 plus delta L. So we'll get d sigma by d epsilon equal to 1 plus E will get, engineering strain will get equal to sigma. So this is given by d sigma by dE equal to sigma divided by 1 plus E. This is known as continuous construction. Continuous construction. Continuous construction is given here. This is done between true stress and engineering strain. True stress value keep increases, reaches the maximum load point here, and then keep increasing like this. If we draw a tangent from this point, ultimate tensile strength value, it will exactly meet at -1. This value is my 1.0 value. This total value is 1 plus EUTS. This is 1 EUTS. 1 plus E. This is 1 plus E. Unstable deformation. If we substitute the necking criteria d sigma by sigma equal to sigma into the equation work hardening rate, we get d sigma by d epsilon equal to n into d sigma by d epsilon equal to sigma. That is at maximum load. So maximum load 1 over sigma into d sigma by d epsilon equal to 1. So we will get n by epsilon equal to 1. So after rearranging this equation, we will get n equal to epsilon, where n is the strain hardening exponent, E is the true uniform strain or strain at the onset of necking. Process of necking. During tensile deformation, strain can be become localized along the length of the sample. The strains are less than the UTS. Work hardening of the material, work hardening strengthens the material and the strain localized relative to the rest of the material specimen. The work hardening rate decreases as the strain increases. At UTS